Swayam Prabha, free DTH channel for education.
vftlab.co.in, and then you can click the differential equations engineers, differential equations for engineers, and the top, like you can go to the lectures and then you can see. So there I have given like the schedule, textbook, assignments, lecture notes, and tutorials, everything. So I have given the schedule for the lectures also. Most probably it is a tentative, so most probably we'll stick to that schedule. And then there will be a there will be an assignment exam. Okay, so I'll be giving an assignment. 2 assignments will be given. It's already available in the website. I'll have an assignment exam. Okay, assignment exam means like whatever is there in the question assignments. From that, I will ask 2 questions for 30 minutes, and then you got to solve that. That is for 10 marks, and remaining part I will just take the marks from the assignments. So the remaining 10 marks from the assignment. Then there will be a written exam on November 28th. So that will be up to Bessel's equation I will be covering. For that, about 20 marks. And then there will be a Viva exam. So for each student, I will spend around 20 minutes. I will ask the question orally, and then you have to answer that. So that schedule I will send it. So most probably it will be distributed on 2 days. So depending on the number of students, I'll just get count and then we'll see. So it will go on 2 days. So every student need to spend at least 20 minutes with me, and I will ask questions and we have to answer. Then I have a tutorials. Okay, so today is supposed to be a tutorial, but I'm just giving that tutorial session on November 6th. Okay, so there I will do the mathematical modeling. So today we will take the class instead of the tutorial. Okay, the Friday class I will make it as a tutorial where we will solve some of the problems. And then so remaining all like we'll have on Monday mostly. So first order ODEs, etc. is there. Then there is 2 assignments are there. Okay, so you can just click the assignment 1 and assignment 2, and then you can see the deadline also I have given. So you need to submit that before the deadline. So you can send it to me as an email. Okay, so just solve the assignment and take a photograph and then send it to me. That I will consider for 10 marks. So both together. And there are some lecture notes available. Lecture notes I will upload it. Okay, I am just composing the last 2 chapters. Okay, but cheat sheets are available. So this also I'm just writing in different ways. So this is the old one. This is the old cheat sheet which I had, and the new one I will just compose and then put it. So almost 80% is done for that. And textbook, mostly I'll follow the basic book because that is the textbook for you, advanced engineering mathematics. And some of the problems or some of the questions I may take from here. The first question, differential equations by Dennis Zill. So from that book also I will take it. And then other textbook, other reference books are there, like advanced engineering mathematics, and then differential equations with applications and historical notes, introduction to PDE. These are some of the other things. So if you have any doubts on this one, let me know. Okay, so the schedule, exam, assignment, deadlines are there, tutorials, everything I have given in very advanced way. Okay, means a priori I have given. Okay, there is no last minute or something. So you can start solving the assignments if you know the answers already. Okay. So any questions on this? Any clarifications required? Okay. If there are no clarification required, then we'll go to our next part of the lecture. Okay. So this is again we are going to cover one more PDE I will just go cover. Okay. So this is also a PDE. So there are 3 big PDEs which you are going to do. Actually, if you see some of the books, there are 4 important PDEs are there. Okay. If you go to my website, where I have given some more partial differential equation itself is a course. That's a 3 credit course for MSc students. So in that case, I have given 4 important PDEs. One is transport equation, okay, which is given in this way: ut plus AUX equal to 0, or ut plus P dot del U, okay, P dot del U, or du, we used to put du, okay. So du, that means like the del U only, that I mean. Okay, P dot du we used to put. This is called transport equation. So if you want, you can just see my video on that. Okay, how to derive that also. It is there in one of the lecture video. There are other 3 big PDs are there. Okay, so the other 3 big PDs which is important. Okay, this is also a big PD only, like important PDE. So this mostly like if you take any of the PDE course or OD course, so this is very important. These 3 big PDs. One PD we already derived. Okay, that is nothing but ut equal to c square uxx. Okay, this is called the heat equation. We call it as a heat equation. This we derived in the morning. This is called heat equation. Now what we are going to derive is that we are going to derive the wave equation, okay, because that is also part of your syllabus. So that I'm going to derive in this lecture, and then we'll see some of the boundary conditions, etc. So this we have already seen. Okay, this is nothing but ut plus c square uxx equal to 0. So that we have seen. So this is the heat equation which we have derived in the morning, and then so this is the bioheat equation also we have derived. Okay, so that's what we have explained in the morning for the cancer treatment, etc. Now we are going for the wave equation. Okay, so the wave equation, the phenomena is again we are going to take some simple thing. Okay, so there is a video also in the next slide, but I'm just going to describe a simple thing. What we are going to do is that we are going to you assume that you have a guitar or violin, okay, or something like a stretched string starter. Okay, some guitar or violin, some stretched string is there. Okay, so what we are going to do is this string we are just going to perturb. Okay, means you are going to make some string oscillations. Then what you are going to do is that this is going to come like this, and then after some time it will come like this. So this is going to come front and back. Okay, means up and down it is going to move. If I just seeing this. Now what we are going to do is that for this string, okay, once I am disturbing the vibration of string, I am just going to derive what is my equation, partial differential equation corresponding to that. So here what I am going to do is that I am going to denote u, which is nothing but the deflection. So we say this as the deflection. So once I am just making some string movement, okay, so I'm just making the guitar, I'm just trying to tune some music, or I'm just going to vibrate that. What I'm going to get is that I'm going to get some deflection. So here I'm going to define u of x comma t, or u of x comma y comma t in general. Okay, u of x comma y comma z comma t, 3 dimensions, etc. So u of x comma t is nothing but the deflection I'm going to take. Means it is going to move in the vertical direction. Though that I'm just going to say the deflection. Okay. So for example, you can see this one. Okay, you can just take a tabela. Okay, take a tabela or some kind of paper. You take some paper. Okay, and then just make some kind of tie it together. Okay, or just take some balloon and put it in some glass or somewhere, tie it, and then make some disturbance over there. Then you can see that it is going to oscillate. Okay, so that is nothing but a elastic membrane which you are stretching in a rectangular membrane. Okay, like the one which is given in the picture. There you are going to perturb the membrane. Perturb means I'm just going to disturb the membrane so that it is going to oscillate. So the vibration is going to be, the surface is going to be vibrated. So in that case, if it is a 2-dimensional case, in this case, I'm going to denote it as u of x comma y comma t. Okay, u of x comma y comma t is nothing but the deflection of the membrane from rest at x comma y and at time t. Okay, so here in the case of violin string, it is going to become like only one variable I'm going to take, u x only I'm going to take, u of x comma t. Okay, with respect to space, I'm going to take only one variable. With respect to time, I have another. So means it is a deflection from the position at x and at time t. That is nothing but the deflection. Then what we get is that we get a surface. So once it is moving, what we will have is that you will have some kind of animated things will come. So the surface is going to disturb, and then you are going to get that. So I can see that the figure where it is getting disturbed, and then you can see that it is moving. Okay, the oscillation is happening here and there. So that is nothing but the shape of the membrane at time t. So whenever the Once you disturb the membrane, it is going to oscillate. So that is happening over there. Now, how do we derive this one? Okay, for this, what we are going to use is that we are going to use the Newton's second law or mass conservation law we are going to use, and then we are going to define that. So now, if I just say this is a violin string, this is tied at two places. Okay, one is at the, so suppose you have a violin or a guitar, you can see that there will be some chord will be there. So three ABC, I think ABC, some chords will be there. So that chord it will be attached over there, and the last at the bottom also it will be attached. So there will be a tension, means it will be tightly stretched, and then there will be a tension will be there. So the tension is nothing but a force. So it's a vector. So it have that, therefore it will have two components will be there. One is the horizontal component will be there, another is vertical component will be there. So T of x comma T, I'm just going to denote the tension. Okay, tension in the tension. Okay, the tension is in the string. Okay, string offers no resistance to bending, so it is having some tension. Okay, so we are going to consider again here. What we are going to consider is we are going to consider only a small interval. Okay, x and x plus delta x. Therefore, at x, I have a tension that I denoted as T of x comma T. Okay, and x plus delta x, I will have another tension. I just notice T of x plus delta x comma T. Okay, so there are two things I have just denoted. Now, what we are going to have is, so once it is having, so I'm just going to concentrate only a small portion of this. Okay, for example, here I have this portion. I'm just going to take only small portion. So in that case, I have a curve here. Okay, I have x somewhere here. Okay, I have a x here. So this is x here I have, and then I have something like delta x is here. Okay, x plus delta x is here. Just notice delta x here. Okay, because I'm just using the notation delta x, capital delta x here. Don't confuse this delta with this delta. Okay, this is a Laplace operator. This is a small delta I'm just doing. Okay, so that's the reason this is delta. Okay, now what we have is if I have some angle. Okay, so this is T is there. So this T I'm just going to resort into two components. One is tangential component. Sorry, one is horizontal component. Another is vertical component. So in the horizontal component, you will have something like sine will come, and the vertical component will have something like cos will come. Now, what we are going to do is that we are just going to derive something like the angle of deflection. We are trying to angle between the string and the horizontal position. So initial position is this one. Once it is deflected, it was having some angle. Okay, it is making some angle with this horizontal one, the initial rest position. So I'm just going to denote that as theta. Okay, theta is going to denote as the angle between the deflected one. Okay, the angle between the string deflected one and the horizontal line, means at the initial position at x and time t. Okay, that is nothing but theta of x comma t. So then what I have is I have the t. Okay, so t is there. So t of x comma, here I have something like t of x comma t is there. Okay, here I have t of x comma t, and here I have t of x plus delta x comma t is there. Okay, t of x plus delta x comma t is there. So then here if I just measure what is my theta. Okay, so this is going to be like theta of x comma t. And if I measure over here, okay, so in that case what I'm going to get is that I'm going to get something like theta of x plus delta x comma t is equal to. So now u of x comma t is nothing but the deflection. Therefore, this is going to denote me the u of x comma t. Okay, this is going to denote me the u of x comma t. So then this is going to be, this is nothing but delta x. Okay, so what is this one? This is going to be delta u. Okay, this is going to be delta u. This is going to be delta x. Now, what we are going to do is that we are going to use the Newton's second law. Okay, what is Newton's second law is saying? What is the Newton's second law? Anyone?
Rate of change
of momentum is called the force applied.
Okay, so force is nothing but we can say like force equal to ma. Can I say this one? Force equal to mass into acceleration. Okay, so what we are going to do is that we have to find the mass of the string. So mass is nothing but the rho. I'm just going to denote rho of x. Rho of x is nothing but the mass density. Okay, mass density of the string at position x. That I'm just denoting it as rho of x. So what we are going to do is that we are going to do the vertical movement. Okay, I'm just going to assume that the horizontal component is going to be not only vertical component is going to be the deflection. Therefore, I'm just going to resolve that. Okay, how am I going to resolve that? Okay, so I have some kind of further assumption because we are going to develop the mathematical modeling. Once you are developing the mathematical modeling, we will just assume some of the things, and then we will develop, and then we will remove the assumptions, and then we will add that as a later stages. So since we are developing a simple one, I'm just taking a tiny element, okay, and I'm just going to take all these things. So the tensor pulling to the right side. Right side means I am just telling this x position, okay. So here the tensor pulling at the right side, I'm just going to denote it as t of x comma t, okay. And the other one I'm just going to denote as the left side I'm just going to denote as t of x comma t. Right side I'm going to denote it as t of x plus delta x. Okay, that's what I mean here. And I am assuming no external forces are there. If there are external forces, then you have to incorporate wherever I strike out. Okay, the strike out place you need to work out, and then you can get a different thing. Now rho of x is given. Okay, rho of x is given. Now we need to find what is other mass of the element. Mass is nothing but rho into volume. Okay, here we are having only one dimensional. So here volume, I mean the arc length. Okay, only the arc length. What is the arc length is going to come? Okay, so if it is very small element, this is going to become like I just measured the arc element. So this is perpendicular. Therefore, you can use the Pythagoras theorem, and then you can find what is this one. So this is going to become like delta x square plus delta u square the whole square. Sorry, square root. Okay, square root of delta x square plus delta u square. So therefore, the volume is going to become the mass is going to become like, okay, mass is nothing but density into volume. Here volume means I'm just denoting only the arc length because it is a one dimensional. Okay, if it is a two dimensional, it will become a surface area. If it is a three dimensional, it will become like a volume, etc. Okay, so this is nothing but the volume here. So rho of x into delta x square plus delta u square is going to come. Now what we have is that force is nothing but mass into acceleration, right? So therefore mass I have, okay, acceleration, that is u is nothing but the deflection unit. Therefore, if I just take the first derivative with respect to time, that is going to give me the velocity. Second derivative is going to give me the acceleration. Therefore, force equal to ma is going to become like utt is going to come. Okay, rho of x delta x square delta u square. This is nothing but the mass, and a is nothing but utt is going to come. Now we know tension is also a force. Okay, so that also should be equivalent to that. So in tension, actually we have two components. One is tangential component, another is one is the horizontal component, another is vertical component. What we are going to assume is that there is no horizontal movement is there. Therefore, what I am going to assume is that t at x comma t, okay, I am just resolving in the horizontal component. So cos of x comma t, okay, is same as t of x comma t cos of x plus delta x comma t, both are same. Okay, these two are same. That I am going to assume. This is constant I am assuming. So that means I am just assuming only the vertical moment is there. So therefore I am resolving only the vertical part of it. So in that case, what I will have is that I am just going to find the net difference. Okay, net one I am just going to calculate. So in that case, in this interval, what I am going to get is that I am just going to get that the difference between these two. So that is nothing but t of x plus delta x comma t into sine of x plus delta x, okay, comma t, so sine theta. So here also theta is there, okay, theta is there. Sine theta of x plus delta x comma t minus t of x comma t sine theta of x comma t is there. So these two are equal. Okay, these two are equal. Now I can just divide both sides by delta x. Okay, so then this is going to become like rho of x into square root of 1 plus delta u square by delta x square equal to. So this I am just going to write it as. Okay, I'll just erase everything. I'm just going to write this one as t of x plus delta x comma t into sine theta of x plus delta x comma t minus t of x comma t sine theta, okay, divided by delta x. So this is going to become delta divided by delta x. Okay, So if I allow delta x tends to 0, okay, means I'm just shrinking small, very, very small, then there you are going to get the differential equation. So we are going to get dou rho of x into square root of 1 plus dou u by dou x square, okay, 1 plus dou u by dou x square equal to, this is going to become like dou t of, okay, dou t of is going to come. Let's see. Okay, so it is going to become like dou t of x comma t into sine x comma t, because I'm just treating this everything as something like let's say g of x is nothing but g of x comma t is nothing but t of x comma t of x t into sine theta of x comma t. Then this is nothing but g of x plus delta x sine theta of x plus delta x is going to come. Okay, that is g of x plus delta x minus g of x comma t. So that together I'm just denoting it over here. Okay, divided by delta x, dou x. So this is partial differentiation. Now we got to resolve. Okay, we got to resolve some more terms. So what we are going to do is that we are going to find what is ux. Okay, from this one we have already that if I just calculate what is my delta u by delta x. Delta u by delta x is nothing but sine theta, tan theta x. Okay, because this is, if I just take theta, this is opposite side by adjacent side. Okay, so therefore you are going to get delta u by delta x is nothing but tan theta. Okay, tan theta is going to give you tan theta of x comma t. If I allow delta x tends to 0, what we are going to get is that this is going to become like, as x tends to 0, this is going to become like, okay, limit delta x tends to 0, because I'm just measuring at x comma t only. Therefore I got allow delta x tends to 0 here. Okay, limit delta x tends to 0. This is going to become like dou u by dou x. That is nothing but ux. Okay, if tan theta is ux, what is sine theta? Okay, so here theta is there. Sine theta is nothing but, I can write it as opposite side by, okay, opposite side by, I can just write it as 1 by this one, 1 plus ux squared. How do we get this one? So tan theta, ux is tan theta, and then if you take 1 plus tan square theta, you are going to get it like secant square theta is going to come. So you just get that, if you just bring it over there, what you are going to get? You are going to get cos plus cancel, and you are going to get sin theta is going to come. Okay, so that's the one. Now if theta is very, very small, okay, if theta is very, very small, what it is going to come? Your ux is going to become like very, very small. If ux is very, very small, what is going to come? Your ux square, 1 plus ux square is almost equal to 1 is going to come. So in that case, okay, if ux is very, very small, if theta is very, very small, okay, theta is very, very small, then your sin theta is going to become like ux. Okay, that is going to become like ux. Now we are assuming that you are having only transverse direction. Okay, so here we have already did that t of x comma t cos theta x etc. is constant. So I'm just going to take this out. Okay, then what I'm going to get is that the t, I'm just assuming it is only function of it is in the transverse vibration. Therefore, I'm going to assume that t of x comma t is a function of t only, not with respect to x. So in that case, what it will become? So this already become like dou t of t, okay, into ux by dou x has come. So I'm just going to take this t out because it is with respect to x only. So t into dou ux by dou x, which is nothing but t into dou square u by dou x square. Therefore, what you got is that, and also we made an assumption that ux is very, very small, less than 1. Therefore, this side also what it will become is like, it is going to become like we are going to get only, sorry, here one mistake we made. I just forgot to write this utt. Because f equal to ma, utt is there, right? So utt is there. So therefore, what it is going to become? Rho into utt, okay, rho into utt equal to t into dou square u by dou x square is going to come. Okay, that's the two thing. So utt is there. So this is nothing but your utt, rho into utt. So I just bring that on the other side, t by rho I can write it. Okay, uxx. So this I call it as c square. Okay, so this is called wave equation. Okay, where c is nothing but square root of t by rho. This is called wave equation. Okay. Okay, so now we are slowly moving to find the solution. Okay, possible. Let us see. Okay, so for example, if you take this wave equation, what are the solutions possible? X square plus t square. Is it possible for a solution for this one? Is it possible for some constant c? Is it possible? Because if you take x square, okay, first derivative if you take it with respect to x, it is going to become like 2x. Okay, so ut, if you want to find ut, so u equal to x square plus t square. If you want to find what is your ux, this is going to become 2x, and if you find uxx, that is going to become like 2. Okay, and if you take ut, that is going to become like 2t, and utt is going to become like 2. Okay, so in that case, what you are going to get, if I'm just finding utt is equal to, suppose I want to find utt is equal to uxx, if I assume c is equal to 1, okay, if I assume c is equal to 1, then this is going to come. Okay, this is going to come. So if I assume c equal to 1, in that case, x square plus t square is a solution for this equation. Use utt equal to uxxx. Similarly, if you assume c is equal to 1, and then we find u equal to cos 4t sin 2x, again almost you are going to get a similar kind of expression is going to come. Similarly, for other variables you are going to get. Okay, so the c you can change it. Okay, so depending on this one, what I'm giving here is that you just solve this equation. Okay, just take the derivative of this u with respect to t and x, then you will get some different c's will be coming, and these are all going to give you some kind of solution for that. Now, if you just make that c adjustment, then what you will get is that you will get many such solutions will be there. It is not only unique solution, you are going to get many such solutions is going to come. Okay, because you can change that. For example, in the case of this one, utt is equal to, okay, utt is equal to uxx. So this is one solution, right? Suppose I, instead of x square plus t square, I'm just keeping some constant, okay, some a into x square plus t square. So in that case, this is going to become 2a, and this is also going to become like 2a. Okay, therefore 2a equal to 2a, so it is satisfied. This a I have chosen arbitrary, therefore we are going to get infinite number of solutions is going to come. We are not going to get only unique solution. Okay, same thing. If you go for the two-dimensional case, then instead of uxx, you will get one more term. Okay, that is nothing but uyy you will get. So instead of uxx, you will get one more term, which is uyy also will come. So if I go for three-dimensional, you will get uzz. So these are all called wave equation. Okay, just keep this in mind, because we will try to solve this equation at the end of the course only. Okay, so till that time, please keep this in mind. Okay, these are all the wave equation, heat equations. Okay, and then another big PDE is called Laplace Poisson or Laplace equation. So in Poisson or Laplace equation is a particular case of this wave equation or heat equation. So this is the heat equation. So we have derived in the morning heat equation. So the difference between heat equation is that, so you put ut is equal to, okay, some k into k square into, okay, uxx plus uyy plus uzz. Okay, if it's a three-dimensional case, this is called heat equation. In wave equation, 1t, okay, extra t will come. So c square into uxx plus uyy plus uzz. Okay, so this is called wave equation. This is heat equation, this is wave equation. So Laplace equation and Poisson equation are particular case of this equation. For example, if I just assume ut is something like independent of t, some function is there independent of t, then in that case what it will become is like uxx plus uyy plus uzz equal to some function of x comma y comma z again. So I'm just assuming that u is independent of t, it is function of x y z only. Okay, so I'm just going to get something like this one. Okay, so ut will not be there, so instead I'm just going to add some other term. So this is called Poisson equation, or simply if you see some of the books, they used to write del u equal to f. Okay, this is called Poisson equation. Same thing here. Okay, utt is there, so instead of utt, if I just replace it some function of x comma y comma z only, that is called Poisson equation. Now suppose u is completely independent of time. Okay, therefore ut will become 0, utt also will become 0. So in that case, what you will get is that you will get del u equal to 0, or uxx plus uyy plus uzz equal to 0. So this is called Laplace equation. Okay. So if f is not equal to 0, that is Poisson equation. If f is simultaneously 0, that is called Laplace equation. Okay. That's what we have here. Okay. So if dou square u by dou x square plus dou square u by dou y square equal to f of x y, then you can see it. You can see the graph also, like how the animations are working for the Laplace equation. So you can verify that if you substitute this u equal to y by x in the you take the double derivative of this, and then you can verify that f is going to satisfy that. Okay, then u equal to f is going to be satisfied. So these are all for your kind of answer. You can just work out that, and then you can see that this is going to be the solution. Now same thing, if you take the Laplace equation, so dou square u by dou x square, so you can see these are all the solution of this equation. So if you take x square minus y square, take the double derivative with respect to x, you are going to get 2. If you take double derivative with respect to y, you are going to get minus 2. Therefore, 2 minus 2 is going to get cancelled. You are going to get like 0 is going to come. Same thing for e power x cos y. If you take the first derivative, second derivative, it is going to be e power x cos y only. Whereas if you take the with respect to y, first time it will become like minus 1 by, second time it will become like cos y. Therefore, minus e power x cos y minus e power x cos y going to get cancelled. You are going to get. Same thing you can verify for the rest of it. Now, if you go for the three-dimensional, again you can just take this one and then check whether it is going to satisfy or not. Okay. Now what we have is we need to get some kind of unique solution. Okay. So if you compare, so these are the three big PDEs I have. So this is one ut plus heat equation, which is ut is equal to, I can just write a simple term. So ut is equal to, I'll just write it as ut is equal to k into del u or k square into del u. Okay. ut is equal to c square del u. Okay. And del u equal to f or del u equal to 0. So these are all two family and this is different family. Okay. So these are all the three big PDEs. These are three big PDEs. Okay. Now you will be come across these kind of equations whenever you solve some of the civil engineering problem or mechanical engineering problem or electrical engineering problem. So if you go for the mechanical engineering problem, one of the thing is like that string bar problem. Okay, the bar problem you will be having. So in that case, it will cover a similar kind of thing. And if you go for the civil engineering problem, where they will be drilling some bore and then they will be taking some water out of it, right? So in that case, there is a theory called Takaki's theory. I don't know the exact name. I think some Soviet or Russian scientist, I think. Okay, so just check that. So there is a theory for that. Like they will just take some concentration of the cement or some sand out of the land. Okay, while they are doing the boring, etc. So that they will have something like this theory. Okay, so that they will be using a similar kind of things. A similar kind of equation they will be solving and then they will speak. Okay. Then what we have is we have okay. So in that case, what we have is okay, for electrical engineering people, they have something called potential equation. Okay, electric potential they have to solve. For that electric potential, once again they will be solving this kind of equation. Okay, sigma del pi equal to 0 or sigma. So this is the one they used to solve. Sigma del square pi equal to 0. Okay, or some function is going to come. Then they will find what is their potential equation. That is going to become like 1 by 4 pi epsilon. Okay, something like epsilon x minus x naught square, okay, in the denominator, something like this. Okay, some rho of r something. So these are the things which they used to do in the potential equation. So if you just remember that, like also this is a particular case. Some of these are particular case for the electrical engineering. Once you are solving for the Maxwell's equation, so if you just use the Maxwell's equation with some particular cases, that you are going to get. Or if you go for the Schrodinger's equation, Schrodinger wave equation, there also you are going to get something. Okay, so but once you come to the real world problem, if you just give this one, as I shown here, there are plenty of solutions are there. Okay, for a single thing, there are plenty of solutions are there. So depending on your choice of your boundary conditions and initial conditions, what you will get is that you will get a unique solution. So in that case, we need to say like what are the boundary conditions are there. So these are the three basic boundary conditions are there. One is called like three Big PDEs. There are three basic boundary conditions are there. One is called first kind, another is called second kind, another is called third kind. So first kind is called a Differential boundary condition or fixed boundary condition. Okay. So in Differential boundary condition, what you have is that you have a domain. For example, I have a rectangular domain. Okay. So in this problem, what I'm trying to do is that either I can solve this ut equal to k del u or ut is equal to c square u or del u equal to f or del u equal to g. That I got solve. So for example, I am assuming the Laplace case. Okay. So suppose I specify del u equal to 0 inside the domain. Okay. And I'm going to specify what is my u. Okay. At this domain means u of x comma. So this is varying with respect to x where y is constant. Okay. U of x comma 0. I just put it 0. Okay. I'm just going to make it less clear. This is 0 and this is with respect to x-axis it is okay this. So you have x comma 0 equal to, I'm just going to specify some f of x, okay, f1 of x, and you have, let's say this is at 1, okay, this let me call it as 1. You have x comma 1 equal to f2 of x, okay, and you have 0 comma y equal to f3 of y, okay, and you have, I'm going to denote this as 1. 3 of 1 comma y equal to f4 of y. Means what I am specifying is that at that location. So all these location, okay, at the boundary, I am specifying exactly what is the values. Okay, exactly what is the value I am specifying. Therefore, they are called fixed boundary condition, or in other words, they are called as Differential boundary condition. Either it is called as fixed boundary condition, or Differential boundary condition, or boundary conditions of the first kind, or also they call it as essential boundary condition because this essential boundary came to the picture because of finite element method. Because in finite element method, if you do the discretization, what you will do is that you will be using the divergence theorem, and then you will just translate from one integral. You will just throw that to other, and then you will get that. So in that case, due to the divergence theorem, you will get one normal derivative will come. So that normal derivative will occur naturally in the finite element discretization. So therefore, that condition is called natural boundary condition. Whereas this one, you have to impose that. Okay, you got to enforce this condition on that to satisfy that. Therefore, this is called essential boundary conditions in terms of finite element method. That's the reason it's called essential boundary condition. So in case of this heat equation, okay, so you can just specify T is equal to F. Okay, so that is also called Differential boundary condition. Means you specify what is the, for example, I have a rod. Okay, I have a rod, and I'm just going to transfer. I have this is going to satisfy this equation. Ut is equal to k into uxx is going to be satisfied. Okay, then here I'm going to specify some boundary condition. Okay, I'm going to specify what is the condition at t of x comma or t of 0 comma t. Okay, and t of, let's say this is of a length L. T of L comma t I have to specify at each time. So this is called Differential boundary condition. Okay, this is called Differential boundary condition because I'm just specifying what is the value here. So I can just specify this is 500 and this is 300. Then I can see that this is going to flow. Then we can see what is the temperature difference, etc. Now the second one is called Neumann boundary condition. So Neumann boundary condition, what we are going to say is that this is also sometimes called as no-slip boundary condition. Okay, so this is like this is what we are specifying here is that instead of ux comma 0, here what we are going to specify that we are going to specify the normal. Okay, so for each one I will have some normal is there. Okay, so for example, if I take this domain, I have a normal here. Okay, I have a normal. So I find what is my dou u by dou n. Okay, dou u by dou n I got to specify. So this one can be like f1 of x, and here I will specify some dou u by dou n. Okay, so this also I take the normal derivative. Here I can take the normal derivative dou u by dou n. Okay, here I can take another normal derivative dou u by dou n. Okay, so this is going to be like dou u by dou n. This is respect to x, so you will get a corresponding thing. Similarly, this is corresponding thing. Means you have to take the normal derivative with respect to this. Okay, outward order. So this n is denoting that this n is a vector outward order. So dou u by dou n, what I mean is that, so dou u by dou n is nothing but n vector, okay, n vector dot del u vector, okay, del u vector. So n vector dot del u vector is called the dou E by dou A. Okay, for example, here, what is the normal corresponding to this one? What is the normal corresponding to this line? Normal vector corresponding to that?
Downwards.
What is the, yeah, what is the normal vector is going to be? It is a unit normal vector. Okay, so either it's B, 1 or 0, you can define. What is the normal corresponding to this one? So for all these things, if you just say, I will just write, otherwise you just take it as an exercise. Okay, find out what is the normal corresponding to each of this plane, okay, each of this line, each of these 4 lines, and then take the dot product with this one. This is very simple. N dot, you are going to get dou E by dou X and dou E by dou Y. Okay, dou E by dou X and dou E by dou Y. Therefore, if it is N is, I am just leaving it as an exercise because no one has answered now. So what is N vector? So N vector, you have to find it. Okay, suppose my N vector is nothing but 1, 0. Okay, for some of these it is going to be there. Okay, if it is 1, 0, then that dou E by dou N is going to be only dou E by dou X. Okay, dou E by dou X is going to come because 1, 0 into dot product is going to come. So I just leave it as an exercise. Which one? You can just find it easily. Okay, suppose N vector is nothing but minus 1, 0. Okay, for some of these it is going to again come. In that case, your dou E by dou N is going to become like minus dou E by dou X. Okay, so these are all the boundary conditions. Similarly, you can go for N vector is equal to 0, 1 and N vector equal to 0, minus 1. Then correspondingly, we will get dou E by dou Y and minus dou E by dou Y. So these are called Neumann boundary condition. And this dou E by dou X will automatically occur once you are doing the finite element discretization. Okay, it will occur naturally. That's the reason it is also called as natural boundary condition. Also, you have second kind. It is also called a second kind boundary conditions of second kind. Then we have one more thing called Robin boundary condition. So the Robin boundary condition is the linear combination of Neumann and Differential boundary condition. Okay, so here I have dou E by dou N equal to F. So Robin boundary condition, I have a linear combination of this one. So I just multiply alpha into U, okay, plus beta into dou E by dou N equal to some F. Yeah, some. So in this case, if I put alpha equal to 0, beta equal to 1, automatically this will become a Neumann boundary condition. If I put alpha equal to 1 and beta equal to 0, then this will become like a Differential boundary condition. Okay. So this is called Robin boundary condition, means you are giving a linear combination of both. So that is called Robin boundary condition. There are other boundary conditions available. For example, there is a mixed boundary condition. You can define, okay, for example, you can define U equal to F here, okay, and dou U by dou N equal to F1, F2, etc. on the other side. So in that case, this is called mixed boundary condition because you are mixing Differential and Neumann boundary condition. Okay, also you can put alpha plus dou U. So at one place, one condition, another place you are putting another condition. So in that case, that is called mixed boundary condition. So those are all not given here. So we can just refer some of the text. So other boundary conditions, like once you are having something like a flow is happening, where you will have something like inlet condition, outlet conditions will be there, and then sometimes you will have something like a periodic conditions where you can see something like a Fourier series, etc. will be using. Okay, so those kinds are there, and then you have wall condition, pressure condition, and symmetry condition, axis symmetry condition. So these are some other boundary conditions. So I just leave it as an exercise, just explore it and then check it what is there. Okay, so now last 5 minutes, I'll just explain what is the last 10 minutes. So I'll just explain what is the boundary conditions which we applied for our cancer treatment problem, which we derived with the model. Okay, so in that case, what we are going to do is that we are going to do use the Newton's law of cooling. Okay, in the Newton's law of cooling, what we are going to do is that we are going to use plateau. Okay, there is a plateau is there. So we need to derive the boundary condition. So as I said, we have different conditions are there. So on the lever geometry, I am going to use the Differential boundary condition. So you have a lever geometry. Okay, you have a lever geometry. Okay, so in the lever geometry, what I am going to use is that I am just going to use T is equal to some constant, means our body temperature. Let's say 37 degrees Celsius or 273. No, sorry. 310 Kelvin, okay, 310 Kelvin or 37 degrees Celsius. So this is the one which we use for the liver geometry. But in our problem, we are taking only sphere. Okay, I'm not solving the entire liver. I'm just solving only the sphere. So on the sphere geometry, I'm going to use the Differential boundary conditions. Means I'm just going to take T is equal to 37 degrees Celsius or 310 Kelvin. Okay. Whereas we have something inside. So I have some vessels here. Okay, some vessels are there. Okay, so it was having some kinds of vessels are there. So for that, I have to define some boundary conditions because the vessel is going to give me some cooling effect. So for that, what I'm going to use is that I'm going to use the Newton's law of cooling. Okay, Newton's law of cooling. So the Newton's law of cooling, what it is going to say is that it is going to give you the surrounding temperature, okay, the surrounding temperature and the body temperature, how it is going to react. So that relation is going to give. So for that, we are going to do. So why we require? Because we have a blood flow. The blood flow is something like the flow is occurring something like bulk movement is going to come. Okay, the bulk movement of molecules, the fluid is going to come from. This is something you can compare with molten rock. It is like comparing apples and oranges, but I'm just comparing because how it is moving. Okay, molten rock, like how it is flowing from the volcanoes, etc. The same kind of things. Our flood is going to come from that. Okay, so that is because both are almost like a convection. Okay, blood flow is also going to be a convection. The molten rock is also going to be a convection process. That's the reason I'm just comparing it. But it is like blood flow is like a post convection. Okay, post convection means our cart is pumping and then it is going to do some kind of jobs and then it's forcing that sinusoidal things or something and then it is going to occur. So that is forced convection. Okay. So convection, what does it mean? So the convection is happening means like the process by which the heat travel through the fluids, or we can say that it is a process of heat transfer. Okay, it is a process of heat transfer through the fluid by pulp motion. Because the pulp motion is going to happen, I'm going to get some convection is going to appear. So in that case, the linear convection is actually directly proportional to T minus T infinity, okay, where T is the unknown temperature and T infinity is mostly the surrounding media. Okay, the surrounding media. For example, in the morning we have seen the cup of coffee. So that cup of coffee in the murderer problem, okay, that kettle gas cap. So how it is getting cooled because we have an ambient temperature of the surrounding media temperature is there. That temperature I denote as T infinity, okay, and then I have a T, which is nothing but the temperature of the kettle or the one which is present in here, and then I find that what is how fast it is going to change. So the heat flux is the linear convection is saying that the heat flux is directly proportional to T minus T infinity, and I introduce a constant called specific heat convection coefficient. Okay, so in that case, my Q. So this is the one which you might have seen. So Q is directly proportional to T minus T infinity, and then you will introduce the constant called the convection coefficient. So therefore, Q is going to be Kachin to T minus T infinity squared. So this is the same thing which you may have seen in the convection boundary condition, like Newton law of cooling effect, which you have seen. So in that case, what you are going to get is that your problem is going to come like the Newton's law of cooling effect, which is going to tell you that the rate of heat loss body is directly proportional to the difference between the temperature between the body and the surroundings. Okay, that is nothing but the Newton's law of cooling effect. So in case of only what you are going to get is that you are going to get like heat flux is the temperature one, you are going to get it something like dq by dt equal to minus HA into is come. Now Q, once again you can go for the, this is nothing but the heat flux, right? So once again what you can do is that this is going to become like dq by dt is going to become like minus HA into t minus t infinity, where A is nothing but the cross sectional area, etc. So what you are going to get here is that you are going to get, again you are going to use the Fourier's law. So if you use the Fourier's law in the morning, that we have derived like k into q, j is proportional to etc we derived. So in that case we have derived dou j by dou x equal to, you can just derive that dou t by dou x equal to. Okay. So 1 by q, 1 by 8 dq by dt is proportional to minus k into dt by dx, which we have derived in the morning. Therefore this can be replaced as, okay, this I can replace it as, this one I can replace it as k into dou t by dou x. Okay, k into dou t by dou x equal to HA into t minus t infinity is going to come. Okay, so this is called the condition for me, this is the condition for me in the case of one dimension. If you come for the two dimensional or three dimensional, this is going to become like dou t by dou n. Okay, so this dou t by dou x is coming because I have a one dimensional one where the normal vector is going to be only the one in the x coordinate is going to become like one, so only one is there, so therefore you are going to get dou t by dou x. If you go for the 3D or 2D, you will get dou t by dou n. Okay, that is going to come. Now, last one. So this is the entire system for me to solve. Okay, this is the entire system for me to solve. Where we have heat equation. First one is heat equation. Second is due to the Newton's law of cooling effect. Okay, the boundary condition, which is nothing but a Robin boundary condition, and then the third one is Differential boundary condition. Okay. Apart from that, this is the complete system we need to define. Okay, this system. What we have is that. See, once I obtain the temperature, once I solve this problem, I will obtain the temperature. Now I got to tell you got to tell me whether you are having whether the cells are dead or alive. So this is exactly same as our COVID-19 model. Okay, in the COVID-19, we have some model called SIR model or SIRD model, etc. is there. So if I just take any person, okay, there are three things are there. One is called susceptible, another is called infected, another is called recovered. Okay, in the recovered, I will just include the both person who has recovered as well as died. Okay, so both are things I just called as recovered. Okay, R denotes them. So S means those who have not gone through that virus, but still they are in the suspect mode. Okay, infect means they are already having the COVID-19 diseases. So if I take any person, okay, in particular time, what they will be is that either there will be a susceptible person or they got already moved to they got already COVID-19. Either they are not affected by the COVID-19. Maybe they will be in susceptible mode, and they are not in the they already got infected, therefore they are in the infected mode, or they may have moved from infected mode to recovery mode. Okay, so this is called SIR model in the COVID-19 cases. If you see, so this is called pandemic model also. We say, okay, the pandemic model. This is the three cases we got. So at any stage, one of them is going to come. So S plus I plus R, I can just denote it as 1. Means if I take any person, he will be at any one of these places. Okay, S plus I plus S plus I plus 1. Now we will have some probability. What is the probability from S to susceptible will move from I? So there is a probability. So suppose you are getting contact with some infected person, so there is a probability that you will just move from S to this basket to this basket. Okay, so therefore you will get the equation of Ts by dt in terms of I you will get it. Okay, in terms of S and I you will get it. Okay, something it will be removed. You will be moving here and they will be removed from here. So you'll get something like added here and subtracted here. Okay. Similarly, if I have Ti by dt, okay, some probability will come here. The person will be moving to recovered mode. Okay, so therefore key is going to go either he will be in recovered mode, okay, or key has added because key is here. So he will be here key is minus, here is yes, I think. So then key will be added over here. So you can just check that model. Okay, so key will be here. Then TR by dt, so you are going to get something like R is going to come. Okay, means you are going to get at any stage what we are going to get is that key is going to be in one of the things. So you are going to get some kind of probability over here, and then you are going to solve this problem. Now the same case here. If I take any cell, okay, that cell is going to be either alive or dead at any given stage. So that is going to depend on the temperature. So I have 3 stages here. One is alive, another is dead. Okay. Another is vulnerable. 3 stages will be here. Okay. So at any stage, the cell may be alive or vulnerable or dead. So in that case, it is going to move from here to here or here to here. So A is going to move from here to here. Okay. So in that case, I can just say A plus B plus D equal to 1. So I can just remove this 1. Okay. I just denote V is equal to 1 minus A minus D. I can just create a 2-compartment model, okay, 2-state model. So this is the one which we derived with the help of Afcode University. You can refer that paper. So this is called cell type model that is going to cover it. And this is one for electric potential which we are solving. This is called Joule heat model, we call it as. Okay, this is called electric heat model. And this is another PID controller model. This also. Okay. Now what we have is that we have, okay, we'll come to this in the next class. Okay, so what we have is that I'll just explain this in the next class. I'll just jump to one more slide. Okay, so this is the one which we have. Okay, this is the one which we have, because I just want to say another couple of minutes to say what is the ordinary differential equation. Okay, so that we can solve it in the next class. See, this is the equation which we have. Okay, for example, I have a equation, heat equation, which we take it dou T by dou T equal to alpha into dou square T by dou x square plus g of x comma t is there. Okay, g of x comma t, something is there. Now I have given some boundary conditions, Differential boundary condition and initial boundary condition I have. So I have lower limit, okay, so x lower, xl I denote, and x upper, okay, on the right hand side I just denote x upper. So this is x lower and x upper I am just denoting, okay. So in that case I have given some conditions. So this is called a complete heat equation, which we will be solving at the end of this course, okay. So we have some conditions like T of xl comma 0, T of xl comma 0, or some T, okay, T of xl comma t is going to be there. Sorry, T of xl comma t is going to be there. Okay, some f of x. Okay, f of x, f1 of t is going to come. Okay, and then I have T of xr comma t or xu comma t is going to become like f2 of t is going to come. Similarly, I can define T of x comma 0. I can define. Okay, that is going to become like some g of x or s of x. Okay, these are the things I have. So these are the geometrical representation of what I am explaining. So in between we have, so in right hand side we have some temperature, left hand side we have some temperature, and then in between we have some temperature, and then you want to solve this equation to see like how it is distributed. Now if you just remove the g of x comma t, that's what we will be solving in most of the lectures in our end of the thing. Now suppose your t, okay, the t is completely independent of x. This is completely independent of x. That means what? This term is going to vanish. Okay, this is going to be, so this is t is completely independent of x, means with respect to t, with respect to x it is not changing. Okay, with respect to x it is constant. Then dou square t by dou x square is going to become like 0. Okay, only this is going to be there. Okay, so in that, what I am going to get is that I am just going to take t is independent of x. Okay, t is independent of x. Okay, so in that case, what I will get is that I will get this will become like one-dimensional variable. So I am going to get dt by dt equal to g of t comma t is going to come. Okay, and this is independent of x, so therefore these two will not be there. So I am just going to get only this one, t of 0 equal to some constant you are going to get. Okay, so this one is called ordinary differential equation. Okay, if t is independent of x, we are going to get that. Similarly, so this I can rewrite it as, okay, in terms of y I can write ty by dt equal to g of t comma y I can write it, and then that also we call it as ordinary differential equation. So same thing. So instead of t I am just putting x here, ty by dx equal to g of x comma y, where x belongs to some domain and y of x not equal to y. This is called initial value problem. This problem is called initial value problem. So in this problem, the heat equation, this condition t of x comma 0 equal to s of x. This is called initial condition. These are called boundary condition. This is called initial condition because I'm just specifying at time t equal to 0. Therefore, this is called initial condition. This I am specifying at the boundary of the two places. Therefore, this is called boundary conditions. Okay. So the same thing here. We have this is called initial condition is there. Now instead of t is independent of x. Okay. Here t is independent of x. Okay. Instead of that, suppose t is independent of t. T is independent of t. Okay, time. T is independent of time. Then in that case, what it will come? This is going to become like 0. Dou t by dou t is going to become 0. Okay. So only x is going to be dependent. Then what you are going to get is that you are going to get t square t by tx square equal to, okay, some g of x comma t is there. So I just put that some other function over there. I can write it as g of x comma t is going to come. Okay, t square t by tx square equal to g of x comma t. Okay, this that g and this g is a little bit different. So I either can put minus symbol or the same thing. Okay, so that is nothing but this one. So in that case, this condition is not going to be there. Only these two conditions are there, and this is independent of t. Therefore, I am just removing this one, and I am going to replace this as some condition c1, c2. So in that case, this is called second order ODE. So this is first order ODE. Okay, this is first order ODE. This is second order ODE. Okay, so here we will have two conditions. One is t of xl equal to some constant, t of xu equal to some constant. So this is called boundary conditions because you are specifying the condition at two boundary places. That's the reason it is called boundary condition. That's all. Okay. These are the only things which we have. And in general, actually, it is not necessary t. You can put even the other things also. Ty by dx also you can put it, and then that is also called second order ODE. Okay. So the underlying idea is that the summary of whatever we covered in the last 3 classes is that we have a mathematical modeling. Okay. So we derived a heat equation, we derived a wave equation, and then from that we have the Laplace equation and Poisson equation. So from these things, what we are trying to do is that we are trying to solve all these problems. Okay, we are trying to solve these 3 problems only mostly. But in order to solve this problem, first you need to understand this problem. Okay, how to solve this? Suppose I just solve what is the first order ODE. First you need to understand. Then you understand how to solve the second order ODE. Then you go for how to solve the partial differential equation. Okay, that is the underlying idea which we are doing. Okay, so that is the thing which we have for the entire course. So from tomorrow onwards, we'll be solving the first order ODE and then second order ODE, etc.